Okay, I know that all of you could just read what's on the screen, but I want to talk through a little bit of it and make some points with you. So I already gave away the secret, which didn't surprise anyone, that if you put in this decimal portion that came from that's the decimal portion of the golden ratio, that created the best design. It might have interested you to note, and there's a little note down here, it didn't matter if you put a whole number in front, right? Because the whole number would just be, that's how many revolutions around in a circle it goes. And then the fractional part is the fraction of the full rotation, right? For where the seed would fall. Couple things on here, right? So here is our number 5 that we defined in the last segment. And we noticed that anytime we use these common fractions, they were very poor designs for our plant. All right. And so why is that? And I really like the way they put it here, that the golden ratio, it's an expert at not being any fraction. Okay, we like nice fractions, right? When we're doing our math, our work, we hope for nice fractions. But in nature, if these rotations were nice fractions, that's not good for the plant growth. Okay, we need to use numbers that are what we would call ugly looking numbers, right? Those work the best for the growths of plants. Okay, and so we've talked about the fact that phi is an irrational number, and they show down here, a couple of the other ones. We mentioned these in class, right? Pi and E. So it's a non-repeating, non-terminating decimal, and it cannot be represented as a fraction. Couple other things that are on here. This is another way to derive the golden ratio. I skipped this application because we can't do everything, okay? But I did show you how it relates to the Fibonacci numbers, all right? How if we divide successive Fibonacci numbers, we get closer and closer to this golden ratio, okay? So there is the link then with the Fibonacci numbers and the golden ratio. And to be honest with you, they're talking about this spiral with the 7 arms. I might have to look that up. I'm not even familiar with that, right? 7 arms when we use 1/7. I'll have to look that up. See, I'm learning all kinds of new things in this class. It's awesome. You're never too old to learn new things, right? And just because I'm the teacher in the class doesn't even mean I learned a lot just to come teach it. So we're learning some cool stuff all together. So anyway, let me just look and see if there's other things I wanted to highlight with you. Some of this stuff looks just like the things that I had on slides in class. And I like this point, right? That we don't see this in all plants, as nature has many different methods of survival. Okay, so that's an interesting point. Here's the golden angle. Okay, so in class, I asked you to estimate the golden angle. A lot of you said like 120, 130, something like that. So here's how we get the golden angle. And this does need to get written on your participation handout so that that's my way of holding you accountable today. So I asked how the golden angle was formed. Okay, and if we multiply 0.61803 times 360, we get this larger angle, right? But then the remaining part of that, the 137.5, is what's considered the golden angle. Okay, and so plants, as they turn their leaves, the leaves turn and form out, they typically do that according to this golden angle. And the 0.618 and also the 0.382, right? These decimal portions formed the best sunflower back at the beginning. Okay, and actually, if you didn't notice that you could enter either of these two and get equally good sunflowers, let me encourage you to go back and check that out. Okay, but I think that's what I needed to say for now. So next thing we'll do is watch some YouTube videos where they talk about all the different places we see the golden ratio. It's really amazing how many places this shows up.